Hello everyone and welcome to the third and final STEPS Young Engineers Award webinar. It's the last webinar, but dry your tears. You are nearly an engineer. So far, you have come up with a brilliant idea. You have designed your project with your team. You have drawn your design on an engineer's drawing. And you have built your prototype. So what else do you need to do? Nothing. If it was perfect. But let's just say that it wasn't perfect. How would you make it better? How would you improve it? There has been no great engineering success that didn't start with a great engineering failure. The best engineers are those that can look back at their projects and try to understand what went well and what didn't. They see their failure as a way to use their problem-solving ability. Everyone solves problems every day, so anyone can use their inner engineer to improve their project. Engineering is not just coming up with an idea, it's thinking of ways to improve the idea and the world we live in. Today, we will take great pleasure in looking at how other engineers failed, and we will see how, with the right evaluation, they turned their failures into great successes. We will look at engineering failures, flops, and fascinating findings. Are you ready to join me on the final whirlwind adventure around the world? First, we will go to ancient Greece to see how early attempts at flight engineering were anything from radical to the ridiculous, but definitely not successful, and sometimes hilarious, but not for the poor pilots. However, we will have to wait hundreds of years and travel to England in the 1800s before we meet the man who brought us closer to our dreams of flying by asking the simple question, why are we failing? From there, and because there are no planes yet, we will have to sail or swim across the ocean to the USA. There, we will meet two bike mechanics with a passion for flying and a habit of failing, but whose failures lead to their incredible engineering breakthrough and change the world as we know it. Thanks to them, we can now hop on a plane and fly back to Ireland, where we will use what we learned to evaluate our projects. And finally complete our own engineering challenge. And just when you thought it was all over and you could sit back and relax, you will meet a very special engineer who has also travelled the globe and perhaps the universe, who will inspire you to get back up again and take on the world. Nothing can stop you. Finally, we will be the master of our own destiny by making our own planes and seeing how far we can fly them. But first, let's look closer at how great engineering failures have led to great success. I am going to tell you a story about epic engineering failures, and there is no greater story of epic engineering failures, flops, and risking it all than the bid to achieve the ultimate human superpower, flight. Have you ever looked at the birds soaring through the sky and dreamt of flying? You're not alone. The dream of flying has been around since the earliest recording. At Roman banquets, actors dressed in wings and feathers provided the ultimate in entertainment by flying off the edge of a tower or a wall. As you can imagine, their brief flight usually ended swiftly in their death. This is not something I would recommend for your next birthday party. At the time, this may have been entertainment for some, but it was not particularly useful engineering design or a design for improving the world we live in. However, for hundreds of years, humans tried to copy birds in their quest of glory and mastery of the elements, most often ending in the same fate, a broken machine or pilot or both. But this small safety hazard did not discourage inventors from attempting to achieve their goals. Even up to the 20th century, the idea of man-powered flight by flapping wings was very popular and equally fatal, despite centuries of failures. like this bicycle plane or this bat plane, which not only looked like a bat on the outside, but also had the structure of a bat on the inside. Now, let's jump in our time machine and go back to England in the 1800s, where a young man called George is about to change all of our lives. George Cayley was a Victorian engineer and man of science with a particular interest in flying. He designed many flying machines, with some more successful than others. What separates George from other aviators is that he decided to do something very interesting. He spent a lot of time looking at why his flying machines were failing. He asked himself what went well and what didn't. He wanted to understand how to improve his design for his next model. So he studied birds and how they fly. Then he studied his machines. He evaluated what didn't work and thought about how he could improve. And through this evaluation, he had a breakthrough. George realised that no matter how much flapping we could do or how many lovely feathers we attached, there was no way that a human could lift themselves off the ground. We are simply too weak and too heavy. So he came up with a new design of a plane with fixed wings, so there was no more flapping. He realised that instead of flapping wings, we needed a source of power to get off the ground. But not from a human, from an engine or other form. But engines like we know them didn't exist at the time. This might sound obvious now, but at that time this was really new. He also realised we needed to change the shape of the wings to reduce the force that slowed it down when it was in the air. So he shaped his wings so that they were curved like a bird. He also realised he needed to learn how to control the machine so that it wouldn't roll in the air and then nosedive to the ground. So he added a rudder to help steer the plane. So now, through his evaluation and improvements, he designed a flying machine that was beginning to look less like a bird and more like a modern airplane. However, it couldn't fly yet. It could only glide. Gliding at this point was still very dangerous, and many early pilots lost their lives or got severely injured. Like famous German engineer and pilot Otto Lilienthal, who died when his glider lost control. But his death was not in vain. It had a huge impact on two of the most important aviation engineers. Meet the two brothers, Wilbur and Orville Wright. They were bike mechanics in Ohio, USA, with a very expensive and dangerous hobby, flying. They dedicated their lives to building a flying machine. So much so that neither brother got married. Wilbur said that he did not have time for both a wife and an airplane. But their dedication paid off. They were the first engineers to design and fly a plane that lifted off the ground and flew with control. And neither of them died in doing it. In fact, safety seems to have been their driving force. So much so that they never flew together as a promise to their father. Their approach to flight was very methodical. They read all about the work of other aviation engineers. They looked at what was working well, like the shape of this glider, and what didn't work so well, like trying to add a steam engine to power an aircraft, or the lack of safety and control when flying, remembering the death of famous glider engineer Otto. And so they set about trying to improve on these problems. First, they thought about how to improve the control so that their glider didn't nosedive without warning. They started by using a kite rather than flying their machine themselves. After years of trial, they decided to see if their improvements would work in reality. So they brought their glider for a real test run. But it didn't work the way they wanted. The plane turned the wrong way when they used their new control system, and it didn't lift the way they planned, so at one point the glider nearly nosedived to the ground. They were very disappointed. Did you have that feeling when you were building your prototype? After all those years of money, sweat and tears, for them to fail must have been heartbreaking, and they must have felt like just giving up. But thankfully, they didn't. Instead, they built a wind tunnel in their bicycle workshop, where they were determined to understand why they failed and how they could improve their design. They tested many different wing shapes and wind conditions, and finally they were happy that they had a new design that would work. Now they needed power. But so far, all the attempts of adding power had failed because the engine was just too heavy, like this flying machine that landed in water straight after taking off. So they designed an engine in their bicycle shop that was made from aluminium rather than steel, because aluminium is strong like steel, but also lighter. They named their new machine Flyer, and in December 1903 they decided to bring their new and improved design for a test flight. The brothers tossed a coin to see who would fly, and Orville won. He flew the plane in the first ever powered flight, only a couple of meters off the ground, but this was a huge achievement. Within 70 years of this first flight, engineers had made so many improvements to the original design and the materials that planes were now carrying hundreds of people around the world safely, and even had carried humans to outer space and had landed on the moon. But this next generation of engineers, pilots and astronauts didn't forget the pioneering work of the Wright brothers. In fact, Neil Armstrong even brought a piece of the Wright brothers' Flyer with him on his journey to the moon for good luck. So this was the story of failures and repeated failures, but also a story of great success. It is a story of how clever engineers didn't just give up when they failed, but used their failure to ask why it failed and how they could improve. So now let's look at how you can apply this to your projects to make improvements. Did your prototype turn out as designed? Probably not. And that's okay. Actually, that's great. Now you can investigate, report, and improve. First, let's start with what went well. What part of your design are you happy with and wouldn't change? You can write about this in your report in the project book. Now for the harder part. What didn't go well? What didn't work out the way you thought it would in your design? And don't forget to write about this too in your report. So you have investigated what went well and what didn't. It's time now to ask yourself, if you were doing the project again, what would you do different? In other words, how would you improve your design? Maybe, like the Wright brothers, you would improve some of the materials you chose, or change the shape and dimensions of your prototype, like the brothers did on their wing design. Would you add something new? Or maybe remove something that wasn't needed or didn't work? And if you don't know what you would do, is there someone or another project that could give you an idea or some inspiration? Make sure to tell everyone about what you found in your report so that the next engineers know what improvements are needed. And now you can sit back and relax and congratulate yourselves. You have finished. You have come up with, designed and built your own innovation and reviewed how your project could be improved. You have gone through the steps of a real engineer and completed an engineering project. You must be very proud of yourself and your team. You are now a STEPS Young Engineer. As a STEPS Young Engineer, you know that an engineer is anyone who likes thinking, coming up with ideas and improving the world we live in. You know that everyone has an inner engineer because everyone solves problems every day of their lives. You know that engineering is not just for boys or about machines and dirt. But did you know that engineering is for everyone and that anyone can be an engineer? Meet Fionnuala O'Reilly. She is an Irish systems engineer who works with NASA as a Datanaut. In her job, she thinks of ways we can use information collected by satellites about space and our planet to learn more about making the world better and advancing technology. But in her spare time, she is a beauty queen, but not just any beauty queen. She is Miss Universe Ireland 2019.
Hi everyone, my name is Fionnuala O'Reilly and I am Miss Universe Ireland 2019. I'm a NASA Datanaut, the Director of Space Apps DC, and I'm also a correspondent for the hit television show Mission Unstoppable on CBS.
Fionnuala works in data and systems engineering and has worked for NASA. So I decided I had to ask her the most important engineering question first.
Do I wear my crown around inside my house? The answer to that is absolutely. I sometimes will walk around in my bathrobe with the crown on my head just because I can. And I think it's so much fun. I absolutely love to do it. Sometimes I will sit on the couch eating popcorn, watching some films, and I will have the crown on my head, and I think it's absolutely fabulous.
Wow! I definitely have to try eating popcorn in a crown, although I don't think I'll pull it off as well as Fionnuala. But that's not exactly the picture of a typical engineer, is it? I asked Fionnuala how she manages to marry these two stereotypes so successfully.
You know, I think it's unfortunate that there are these stereotypes about women in STEM and women in engineering. For a long time, I think we've been sold this story that you can't be beautiful, you can't love fashion or beauty or makeup or glam if you also like science or math and technology and engineering. It's just not true. And I think that I'm a testament to the fact that women are multifaceted, and there's so many women out there that I've met, that I've had the opportunity to meet, and they are fabulous in so many different ways. So just because you may like fashion, beauty, any of those things, it doesn't mean that you can't like science, math, or engineering. Go out there and show people that it's okay to have a wide variety of interests.
I couldn't agree more. Fionnuala is a powerful voice for diversity in engineering. Did you notice how in the story of engineering so far, many of the famous and celebrated engineers are men? This is not a coincidence. Let's have a very quick look at the little told story of women in engineering and see if you, the next generation, can change the story. Before the 20th century, women were generally not admitted onto engineering courses in universities, and those that did were given certificates of completion rather than degrees. This picture is the picture of the first women in the world to attend university. The University of London was the first to accept women in 1869, although women were not allowed to get degrees there until decades later. However, this didn't stop some strong women who used their engineering interests to come up with useful or commercial inventions, like Henrietta Lowe, who invented a famous propeller for naval ships at the time. Other women of engineering are hidden in the history books. They are women who had an interest in engineering or science and carried out their work as calculators or assistants, but they were often the driving force. Like Caroline Herschel. She was a German lady living in England who worked with her brother, who was the royal astronomer for the king. She discovered many comets and other celestial objects through her work under her brother. Eventually, her work was recognised, and she was the first woman in England to be paid a salary for work in science. Even though she discovered 8 comets, more than her brother, she was paid for the role of a scientist's assistant. The first female engineer in Europe is widely agreed to be an Irish lady from Well Park in Galway called Alice Perry. She achieved a first-class honours degree in civil engineering from Queen's College in Galway, which is now NUI Galway, in 1906. In the 20th century, women slowly were allowed to enrol in some engineering courses. Now, here's a challenge. Can you spot the woman on this engineering course? There she is. However, changes were very slow and women were few and far between. They were thought of as the curiosities in the class for many years. In fact, the changes were so slow that one famous elite engineering school in Paris only allowed women to join their course in 1972. But even with these slow changes in education and the role of women, we have seen some incredible contributions to engineering. Like Ellen Ochoa. Dr. Ochoa was an electrical engineer who was also the first female Hispanic astronaut to go to space. In fact, she liked it so much, she went back 3 times and spent nearly 1,000 hours in orbit. Another brilliant female engineer who was having a big impact on our life is Anne Aaron. She is a Filipino software engineer and director of video algorithms at Netflix. She is responsible for making sure the 80 million or so Netflix viewers can watch their desired program at a click of a button. These are incredible women role models, but there is still a long way to go for women in engineering, and you are the generation who will make the biggest changes. I asked Fionnuala, why should young girls choose to become an engineer?
I think that girls should pursue engineering as a career because you get to have so much fun and you can work in so many different industries. You get to be creative, you can help people, you can use a wide variety of talents to solve real world problems. Some of the problems that I've seen as a host of the NASA Space Apps Challenge have been very, very interesting, wide-ranging problems that deal with environmental science, earth science, but also space innovation. So there's a wide variety of ways to become an engineer, and there's a wide variety of ways to apply an engineering degree. I think becoming an engineer was the best thing that I could have done because it also has taught me to have a problem-solving attitude in everything that I do.
Yes, engineering is a great way to use your talents to make a difference. I asked Fionnuala where she would like to see women in engineering in 10 years. Yes, diversity in engineering can only have a positive effect on breaking boundaries. Engineering is a way to make an impact on the world we live in and make a change for the better. We have come to the end of the webinar and it's time to look back at the best bits. We looked at how many engineering projects don't go as planned. And we realised that this is okay. In fact, it's a good thing. Failure can lead to successful projects in the future. We learned that engineers look at what went well and what didn't go well in their projects and report on their findings. They use this to improve their designs. In your projects, you should think about what went well and what you would change to see if you can improve your design. We looked at how engineering is for everyone and anyone can be an engineer. We were inspired to be the next generation to bring diversity to engineering and to be the change. So what's next? Well, first, let's meet Caroline Spillane, Director General of Engineers Ireland, who has some final words of encouragement for you.
Hello there, my name is Caroline Spillane. I'm the Director General of Engineers Ireland. I wanted to say congratulations to all of you for entering the STEPS Young Engineers Award competition. You know, you're the next generation of engineers, the people who are going to find creative solutions to problems within your communities, for society, and for the world in general. So well done and best of luck in the competition.
In your final worksheet, don't forget to tell us about your project. You can tell us what went well, what didn't go well, Would you change the design or would you use different materials? How would you improve your project? Before we go, there is one last engineering challenge for you. This is a competition that pits classmate against classmate to find out who is the record-breaking paper airplane engineer in the class. This is the Red Bull Paper Wings Championship in Austria, where competitors compete to win the title of Paper Pilot Champion. This year, the winner was Katarzyna Arafnova from the Ukraine. You will get the opportunity now to hold your own championship, and the paper plane record holder will first show you how to make a proper paper airplane. You will need a sheet of A4 paper, and you can follow along. Teachers, this may be a good time to pause and pass out a sheet of A4 paper to each student if they don't have one. At the end of the video, you can stand up at one end of the classroom and throw your airplanes. The longest throw wins the title and the glory.
Norm, I'm here at Hiller Aviation Museum in San Carlos with John Collins, the paper airplane guy, and you're going to do something really cool. You're going to teach me how to fold one of your designs.
This is actually a classic design. This is designed by E.J. Nakamura. It's called the Nakamura Lock. People may have seen this plane before, and I always suggest people start out with a really simple plane, learn how to fold that, and then, more importantly, learn how to adjust it.
Tweak it.
Tweak it, yeah.
Okay.
So let's go ahead. Let's
All right,
orient
so
the paper.
This is just a regular 8.5 by 11 sheet of paper. You can buy this at any, Kinko's, any photocopy store.
Yeah, we're using yellow because it's just easier to shoot on TV. But this, any old piece of 8.5 by 11, 20-pound copier paper, that's the stuff.
All right.
In fact, if it's been Xeroxed onto, it's even better.
Awesome.
The heat process from the copier stiffens the paper a little bit, and the ink is actually a microfine layer of plastic. Stiffens the paper.
Stiffer. You don't need scissors, don't need tape or anything.
This is just a really simple, fun plane that holds together nicely. So we're going to fold it in half the long way.
Okay.
Some kids always, in my classes, call this the hot dog bun fold. It's helpful sometimes to remember shapes as you go along, rather than what's actually happening folding. So next thing we're going to do is take one corner and fold it down. This is sort of like the old dart that everybody learned how to make. We're going to flip it over and do exactly the same thing with the other side. Fold the other corner down.
And you got to make sure the creases are tight.
Yeah, when I'm making the world record plane, I got a tool that I use called a folding bone, but this is not that critical. This is not going to be a world record plane. It's just going to be a good plane. So we've opened it up, the very first crease that we made, and now you can see that we've got two little triangles on top. Those little triangles make a big triangle, so we're going to fold the big triangle straight down, right on the base of the big triangle. And you can use this center crease to keep it lined up. Just put that top point right on the center,
there.
And that'll make sure that you're folding right straight along there.
Simple enough.
Now, we're going to do something on this plane that I don't do a lot. It's called a rat fold, which stands for right about there. And you can tell there's a high degree of precision involved.
Yeah.
No, not really. We're going to use our thumb and measure up one thumb width and just fold that point that we just folded down up about a thumb width.
Okay.
1 inch is about 22 millimeters. So, if you're really going to measure it, knock yourself out. One thumb width is great. Okay, unfold that. And you can see that we've got the original crease that we made down the center and this new crease right there where those creases meet. That's the bullseye. And X marks the spot. These corners up here, the creased corners, one at a time we're going to put them right on the bullseye. Nothing else is going to line up. So now we do the other corner.
Right on that bullseye?
Right on the bullseye. And now we're going to remake our little rat fold, only you have to make a new crease here. If you use the old crease, you'll probably bunch these layers up. So let's just make a new crease right up over those two corners. Now this is really cool. This plane is called the Nakamura Lock, and E.J. Nakamura, really gifted paper airplane designer. What you're going to see now is the whole plane is going to get locked together by our next move. We're going to follow this crease that's on the bottom layer here. We're just going to pick it up, follow that crease. Look what happens to that little rat fold now. It's locked all the layers together. We've turned it into a three-dimensional locking mechanism from a two-dimensional fold. Really clever idea. Any other paper airplane that you just kind of fold when you just fold the corner down over and over, it flops around, creates a lot of drag. All those layers are busting loose. This, it's all locked together.
Tuck right there.
Two more creases, we got a plane. We just take this long creased edge down to the base. The long creased edge, match it up with the bottom.
Right there.
Yep, flip it over. And if you've missed a little bit, Norman's missed a little bit here. I don't want to get picky, but just to illustrate, if you miss a little bit here, just make the other wing match. It's not totally important that you hit this
as long as they're symmetrical?
Yeah, you just want to make one wing like the other wing. In fact, I tell kids all the time, if you've messed up and you've junked up one side, or you accidentally slipped and kind of wrinkled one side of the plane, do the same thing to the other side.
So as long as a little bit here, I'm gonna try to match that up.
Perfect, there you go. So now what we're gonna do is we talked about dihedral angle before. And if you don't do anything to your plane, you've got negative dihedral angle. If you would like to have a paper airplane that flies upside down, you throw that, it'll probably reliably roll over and fly upside down. If you want it to fly right side up and straight, we lift the wings a little bit. That's positive dihedral angle. And that puts the center of lift up above the center of gravity so that when the plane is flying, you get this pendulum effect from the lower part of the plane that rocks it back to neutral. And the other thing you can do, especially if you're throwing it outside, is give it just a tiny bit of up elevator by just bending the trailing edge up just a little bit. And that, when you throw outside, the center of lift tends to shift back on the plane. The faster the plane flies, the center of lift will shift back, which will cause the nose to go over. So if you're throwing outside or you want to throw really hard, a little more up elevator. Now, the thing about making a paper airplane, anybody can fold this plane, really simple, right?
Yeah.
Not a huge number of folds. So you want to look at the plane overall symmetry, make sure one wing matches the other wing. What do you think when you look at your plane here? You have to really train your eye to be critical. You got to lawyer this plane to death. There you go, now you're lawyering the plane. So if this is bulging out more than the other side, you want to flatten
it out.
this. Yeah, even that out. That gets it to fly straight. And so if your plane then, and after you really do a fine tuning before you even throw it, once you throw it and it's turning one direction or another, you can even fix that. So here's what happens. In order to get your plane to turn left, let's say that we want our plane to turn left, we would bend the trailing edge to the left as you're looking at it. So the nose is that way. If we want the nose to go left, we bend the trailing edge to the left. Now,
This part right here.
yeah.
Bent over. All right.
So now here's why that works. You don't have to memorize this, but here's why that works. The air travels down this side of the plane and hits that little bend. The air gets deflected this way. The airplane rotates around the center of lift. So the air goes this way, the tail goes that way, and since it's rotating around the center of lift, the nose will go left. You don't have to memorize any of that. Here's the secret. Bend this trailing edge the direction you want the nose to go. Left to go left, right to go right.
It's a little rudder.
Yeah, it's a little rudder. So left to go left, right to go right, and these corners back here, or even in, it's better to even do up elevator close to where the wings meet the body of the plane because you get less asymmetrical drag. You create drag more efficiently right in the center. So this is actually the better place to do up elevator.
Now, as opposed to the tip here.
As opposed to the tips, because what you'll do is you'll get one bent a little bit more than the other, and it'll create more drag on one side of the plane, and it'll start to turn that direction. So you'll actually allow one wing to fly faster, and the faster wing will always get out ahead.
Very cool. All right, so that's it.
That's it, the Nakamura lock. Let's give them a test flight.
In a few minutes, you can take your planes to the end of the classroom and see who in the class will be crowned the record-breaking paper plane engineer. This completes our engineering adventure for this year. Best of luck from all of us in STEPS with your competition entries.